to again here. So we had the solids on the leftmost, we have liquids, and then as we move through the saturation dome or the vapor dome, we come out the other side and we have vapors or gases. Between the liquids and the vapors, we have the vapor dome where both phases are present. Between the solid and the liquid, we have the solid-liquid region where both phases are present. So last time I said I labeled two isotherms, those are lines of constant temperature, as TB and TA. And our question to you was, which temperature is higher? If we were to label this arrow as being the direction, in this direction, what is happening to temperature? Is the temperature increasing or is the temperature decreasing? So you could use anything that works for you in terms of understanding these state diagrams is fine. But one thought process you might have gone through would be to say, okay, well, I'm going to sit at a fixed volume here. And as I move, specific volume or inverse density, if you prefer. But as I sit at the specific volume and as I increase the pressure, what's going to happen to the fluid? What's going to happen to the temperature of the fluid? So again, at a fixed specific volume, as you increase the pressure, you're going to have to increase the temperature of the fluid. So the correct answer is that TB is greater than TA. That's not true. And that this is the direction of increasing temperature. Again, so whatever thought process you went through or thought exercise or thought experiment you went through, that's great. That's the best way for you to understand. And assuming you came up with the correct response, that's fine. So however you do it is fine. So what I wanted to do, make this just a little bit more complicated, this figure, is I wanted to add this, the triple line, which I did not have on there before. And the triple line here is where you have all three phases present, hence the name. Triple line, not triple line. All three phases present. And what's kind of a neat thing to just understand is that the drawing that I showed for you, where there's the solid-liquid region actually bumps to the left here, is for a fluid where it contracts unfreezing. And this interface would actually move to the dotted line if we had a fluid that expands on freezing. Now, in energy systems, we typically need to have fluids that move. So solids don't work so well for us, but they're really fun for lots of other systems that we might consider. So I'll say that in thermodynamics, our working fluids, the fluids that actually do the work in terms of power generation, are typically liquids and vapors. So we typically don't operate in this region. Okay, most of our fluids are up here on the upper right-hand quadrant, if you will, of the PV diagram. So this is kind of getting into detail. That's fun, but not really necessary for a lot of what we do. Okay, but I did want to introduce, so that was the PV diagram that, again, we've looked at that for a while. Let's add another diagram to our list of tools. And we use this one mostly just to remind ourselves of all those definitions that we talked about before. So what am I talking about? The pressure temperature diagram. Again, this is the most tactile diagram, the most tactile variables in terms of our understanding. It's very intuitive for us to understand processes and state conditions on PT, pressure temperature diagrams. And so what I just wanted to do was remind you, I'm going to sketch here again a two-dimensional rendering here of the pressure temperature diagram. And here's my critical point. And here's the vapor region. And here's the solid region. And here's the liquid region. So now we have the three phases as identified on our PT diagram, solid, liquid, vapor. So this is just, again, a reminder of, well, if I take a liquid and I transition from a liquid to a vapor, that process is referred to as vaporization. Or if you prefer, it's evaporation. Okay. And if I move from a vapor or a gas, remember I use those interchangeably, to a liquid, then I have a process that's referred to as condensation. If I go from a solid to a vapor, that process is sublimation. And the one that everybody's familiar with, or most everybody's familiar with, is when you take dry ice, which is carbon dioxide. And if you usually people use that for shipping things that need to be kept cold for a long period of time. And if you ever pulled out a bar of dry ice, you can see the vapor coming off it. And that's a very common sublimation example. And of course, if you take a solid and change it into a liquid, you're melting it. You're not melting it, you're melting it. And that gives you, again, some orientation in terms of the PT diagram in terms of common phase changes. So those are all things that I would expect you to be familiar with. That if I told you, well, you have a vapor that's undergoing a condensation process, that you would know that explicitly is going to take you through the vapor dome. So start you outside the vapor dome and then put you back into the liquid region. Okay, or not back into, but put you into the liquid region. Okay, so now we have these great diagrams for our use, and again, they're really meant to give us a pictorial understanding of the states. So we can see that if I know pressure and volume, I should be able to uniquely define temperature. If I know temperature and pressure, I should be able to uniquely define specific volume. So we can move between these different variables, these different thermodynamic properties with ease. Okay, having said that, now I want you to say, okay, let's go back to that PV diagram, because we did a bunch of examples where we used PV diagrams, but there weren't any saturation domes or vapor domes on them, and we didn't look at isotherms and isobars and things like that. But they were there. They're implicit, okay? So take our example that we considered earlier about how we had the two-step process where we were compressing and then expanding air, okay? What we're going to find is that, well, for us to condense air into a liquid takes a lot. You can do it, and I'm sure many of you are familiar with liquid nitrogen, liquid oxygen, and liquid air. Okay, you have to really compress the heck out of it, and you have to drop the temperatures quite a bit. So they're typically cryogenic systems. So that means in that system that we considered before, here is our little example. We said we were going to, remember we did a polytropic compression process from 1 to 2, and then we did an expansion, constant pressure expansion process from 2 to 3. That vapor dome is on that figure. It's just way down here. Note not to scale. Okay? And, again, I'll try and use my different colors here to emphasize this. There were lines of constant temperature on there as well. Or we didn't draw them on there, I should say. But they would look something like this. Okay? So they would have curvature that would be different curvature than the, so these are my isotherms. And they would have different curvature than the polytropic process, okay? So just need to remember that these state diagrams are valid for every substance. Every substance can be defined. Every simple substance, so it's pure substance, can be defined in terms of the state diagrams. Cool. So we talked about isotherms and isobars already. Let's flip. So I just wanted to emphasize again 2 more things. And I promise we'll get off the subject of these phase diagrams because they tend to be pretty dry. Oh, no pun intended. So let's go back to the PV diagram that we talked about before. And again, typically we only consider phase change between liquids and gases because we need to be able to have our fluids moving, and we don't move solids so well, although we can. And so we typically cheat, and we just put the saturation region as a simple dome. Okay, so this is my saturation region. And again, I'll label it as liquid. And here's my vapor. Okay, and then we know my lines of constant temperature in the dome. The lines of constant temperature have to be straight lines because, again, we know that the pressure and temperature are dependent within the saturation region. So this is the saturation dome. Vapor dome, all sorts of names, saturation regions, vapor dome, et cetera, et cetera. So I told you before that if we have a saturated liquid or a saturated vapor, that uniquely defines the state, assuming we know one other independent intensive variable. So if I know temperature and I tell you it's a saturated vapor, and let's say it's this temperature TA or T1, we'll call it here, that defines, if it's a saturated vapor at T1, that uniquely defines the point shown on this graph. Okay? So now I want to introduce that term quality. Quality in thermodynamics has a very specific meaning, and it is in fact a thermodynamic property. In addition to, I hope you do high quality work. So quality is only defined within the saturation region. So quality is defined as the mass of vapor relative to the mass of liquid plus mass of vapor present in the system. And it's given, I misspoke earlier, there is an X in thermodynamics, and that X is the quality. So the X is the variable notation that we use to define quality. You can see that it should be dimensionless because we have mass divided by mass, so it's actually dimensionless like this. And you can see that it's a fraction where if you have a fully saturated vapor where all of your mixture, and by mixture I mean phase mixture, is in the vapor phase, then your quality is equal to 1. And if all of your mixture is in the liquid phase, then that's a quality of 0. So X equals 1 is saturated vapor, and X equal to 0 is a saturated liquid. And so these lines, these isotherms, which are also isobars within the saturation region, are defining this line up to the critical point. That defines the line where the quality is equal to 0. That's the saturated liquid line. And then this line here on this side is the saturated vapor line, where X is equal to 1. Saturated liquid. Okay. So if I were to go at some arbitrary location between these two endpoints and say, okay, well, that's a quality of 30% or 0.3, you would, again, if you have the quality and the pressure or the quality and the temperature, you fully define the state. Okay, so again, we want to emphasize quality is only defined within that dome. Okay, or what we'll call the dome. Okay. So again, we'll keep coming back to these examples of these phase diagrams and how to put states on and how to put our processes on them. But again, I want you to be thinking in terms of the phase diagrams, the units, the sign convention are all cumulative. They're all built and work together to help you understand the system and for you to be able to conduct your analysis accurately with good intuitive understanding. Sorry. I did want to close with one question for you, and that's a question of if you were to, what I want you to do is to sketch what constant pressure condensation looks like on this PV diagram, assuming you start with an unsaturated vapor and end with a condensed liquid. Okay, so lots of words, so I wanted to write that down so you can understand. And they're all meant to cue you to very specific places. So what you, again, draw on a PV diagram. Okay. Condensation from, and I'm going to use this as a teaching moment. This region here to the right of the saturation line, this is referred to as the superheated region. And that has a very specific meaning in that it's superheated to a temperature higher than the saturation temperature. Okay, so that's vapor is at a temperature greater than T saturation. Okay, And if you have a subcooled liquid, so this area is a superheated region, and a superheated vapor is a superheated vapor. Oops, no, I said it twice. Vapor. A superheated vapor is a vapor at a temperature greater than Tsat. A subcooled, so in this region, we're going to define subcooled liquids. So that's the superheated vapor region. This is the subcooled liquid region. And a subcooled liquid is at a temperature cooler than the saturated liquid temperature. So it's at a temperature lower than the saturation temperature of that pressure or that condition. So in other words, you have to be, for a subcooled liquid, you're essentially to the left of the saturated liquid line. For a superheated vapor, you're to the right of the saturated vapor line. Okay? That's a 1. I think that looks like a 1. Okay, so again, let's get back to our question. Draw on a PV diagram. So first of all, always practice good habits. So draw your PV diagram, label the axis, put the dome on there, and put on there your isotherms. Okay, a few examples. Typically, I like 3 isotherms. Okay, so draw your PV diagram, put the dome on your diagram, put the 3 isotherms on your diagram, understand which temperature is higher than the other. So again, these are lines of increasing temperature here. And on that diagram, I want you to draw condensation from a superheated vapor to a subcooled liquid.